This is going to be a talk about runaway stars as possible sources of the elliptical ring structures in NGC 7538. Large ring-shaped gaseous bubbles are often observed within molecular clouds, which are regions in space that are filled with gas and dust. These rings are typically the result of star formation, stellar winds put off by fusion, or stars exploding in a supernova. Two of these rings have been observed in the star-forming region NGC 7538, shown in Figure 1. Each is about 10 parsecs in diameter, where a parsec is a unit of measurement equal to about 3 times 10 to the 13 kilometers. These rings caught the attention of astronomers because they have no visible source, which is unusual given their large mass of about 500 solar masses, where one solar mass is the mass of our Sun. Because these rings are unlikely to have formed without a source, the search begins. Observations of a 1 by 1 degree portion of the region were first made with the Herschel Space Observatory in 2010, producing the image in Figure 2. Then, a detailed inspection of the southern ring was done in 2013, and recently, a more careful inspection of the Herschel data revealed a second ring, the northern ring. So we began our search for a possible source using SIMBAD, which is a database that contains information about stars and their motion. We chose a search radius of 2 degrees around the center of both rings and searched for only high-mass stars, which are referred to as O or B-type stars. These are the stars we considered in our search because only high-mass stars would be capable of creating rings of the size we observe via stellar winds. So from our query of high-mass stars near the rings, SIMBAD returned a list of 85 stars, along with their right ascension, declination, proper motion, and radial velocity, which all give information about the star's distance and motion. A few of these stars can actually be seen in Figure 2, indicated by the green dots. Our next step was to narrow down the list, so we asked the question, what stars can we eliminate as possible candidates? We assume here that the star that created the ring has since moved out of the region. Therefore, from the perspective of Earth, if the observed star is currently in front of the rings, it will be moving away from the region and toward us. Similarly, if the observed star is currently behind the rings, it will be moving away from the region and away from us. So, using each star's distance from the rings and radial velocity, we're able to determine its position and trajectory. And using the determined criteria, the list was narrowed down to 15 possible candidates. To help narrow even further, we want to visualize these 15 stars, as well as the rings in 3 dimensions. So we queried Gaia, which is another database containing information about stars and their motion. We searched for each star's parallax angle. Parallax is the apparent displacement of an object due to a change in the observer's point of view. So as Earth orbits the Sun, a star will appear to experience a small degree of displacement. And using this small angle and some simple trigonometry, the distance from Earth to a star can be determined. And in turn, we can determine the distance from the ring to each star. So, now that we know each star's radial velocity, proper motion, and parallax distance, we can make a 3D plot, which is shown in Figure 3. This shows each star's position relative to the rings, as well as their trajectory in 3D. And assuming that the stars are traveling in straight lines, we can then take their current trajectory and reverse it to show where the stars were at some point in the past and the likely path they followed. That's shown by the black vectors in the plot, pointing back in time. So now let's talk about some theories as to how these rings could have formed. Our first theory is that they were created via bipolar outflows, which are large, powerful jets of gas that are ejected from the poles of a forming star, shown in Figure 4. This theory could support the similar elliptical shape of the rings, as well as them being elongated along the same axis. However, we would expect to see an abundance of carbon monoxide inside the rings, and data from the James Clerk Maxwell telescope reveals a complete absence of any carbon monoxide. Inspection of the southern ring shows very little dust or other material present, and we also don't identify any specific dense objects, such as protostellar cores, to suggest bipolar outflows as the creation mechanism. The second theory is that a star, originating from outside the region, passed through the molecular cloud and created the rings via stellar winds. This theory is supported by other studies that have investigated similar scenarios. And in the case of NGC 7538, this could explain the elongation along a similar axis. The velocity of the star's stellar winds plus the velocity of the ring expansion itself, both acting in the same direction, would result in the elliptical shape that we observe. However, a star simply passing through the region would likely not spend enough time in close proximity to the rings in order to drive the expansion to the size that we observe. Our third theory is that a star, originating within the region, caused the expansion of either one or both of the rings and then traveled out of the region. We theorize that this could have been accomplished one of two ways. Either one member of a binary star system, which is when two stars are orbiting a common center of mass, like in Figure 5, exploded in a supernova and caused the companion star to be ejected from the system, or a binary star system interacted with a third body. So let's expand on this three-body interaction scenario. We assume that all stars involved would be O or B type stars because high-mass stars tend to pair with other high-mass stars. Also because a high-mass star would be capable of causing a strong enough perturbation or disturbance to the system to cause it to become unstable. This interaction would result in a very tightly bound system hurtling through the molecular cloud, and the third body, or the runaway star as we'll call it, moving in the opposite direction and possibly creating the second ring. This is ultimately the theory that we'll be investigating. So in order to continue building the picture of how these rings formed, we needed to investigate the timescales. We hypothesized that a ring could expand to 10.6 parsecs in less than the main sequence lifetime of an O or B type star. Main sequence refers to the phase of a star's life when it's fusing hydrogen and burning fuel, and a star will spend about 90% of its life on the main sequence. But after this phase, when it's no longer fusing hydrogen, its stellar winds would not be strong enough to drive the expansion. The main sequence lifetime of a high-mass star is about 20 million years. Calculations were done to find the equations of motion for radiation pressure expanding a shell, and it resulted in this equation for the time it would take for the rings to expand to a final radius r sub f. We chose different values for the beginning radius r sub naught to give a range of 150,000 to 250 million years, and this hypothesis is supported by two other studies that estimate wind-blown bubbles forming in less than the main sequence lifetime of a high-mass star. So now let's go back to our plot of the 15 candidates. After close inspection of each star's motion with respect to the rings, looking from multiple different perspectives, only one stood out as a possible source, and that's this star here. And you can see from this perspective, it looks promising for having been at the location of the northern ring at some point in the past. This is BD612408. It's a B-type star located 153 parsecs away from the center of the northern ring, traveling at 62 kilometers per second. Figure 6 offers a great perspective of the star's motion that shows it was likely at the center of the northern ring. And now there's some uncertainty associated with the distance of the star from the ring, and this is represented by the black vectors, showing a range of possible trajectories. And the blue circles at the end of the vectors represent the uncertainty in direction of origination, which comes from uncertainty in proper motion. Now that we have a possible source identified, we can compare the timescales to see if it's a plausible source of expansion. We set up a system of equations to calculate when the star and ring were at the same location, and we determined they were coincident about 2.4 million years ago. This is reaffirming because it fits well within our limits of the main sequence lifetime of a high-mass star, which was 20 million years. From this, we can determine the expansion rate of the northern ring as well, which was calculated to be about 4.3 kilometers per second. And we consider this reasonable when compared to other similar structures. For example, the Bubble Nebula is expanding at a rate of about 35 kilometers per second. And an important note to make is that this star's trajectory is along the ellipse's projected major axis, consistent with the shape of the northern ring. So in conclusion, we began with two large ring structures of unknown origin in the star-forming region NGC 7538. We considered three possible formation mechanisms: bipolar outflows, an outside star passing through the region, and a three-body interaction involving a binary star system and a runaway star. We were able to identify one star, BD612408, that met the criteria for having formed the northern ring. We calculated that they were coincident about 2.4 million years ago, and this is about how long it took for the ring to expand to the size we observe. This is consistent with our hypothesis of being less than 20 million years. We did not, however, identify any star whose trajectory is consistent with having created the southern ring, so further analysis of the stars surrounding NGC 7538, possibly with a larger search radius, is entirely possible. And that concludes my presentation. Thank you.